let me share with you what's in it. So we've had 4 very dedicated poster judges that went around and looked in close detail at all the posters yesterday. And so I have 3 awards here for most outstanding poster to hand out to hopefully people that are in the audience. So the first outstanding poster award goes to Catherine Potts. So our poster panel consisted of Jan Medlock from Oregon State, Donna Colhoun, Donna here, from Idaho, from Boise State, and Bethany Lush from Oregon National Laboratory, and who did I mention? And Chris Curtis from San Diego State, right there. The second outstanding poster award goes to Yibo Yang. Is Yibo here? Okay, well, let's give him a round anyway. And the third and final outstanding poster award goes to Stephanie Hare.
Today's plenary talk will be given by Chris Jones, who is the Field Path 3 Distinguished Professor of Mathematics at UNC. As I've been telling people, Chris is one of the few movers and shakers in our community. He organized this and created this math climate research network. I think you coined the phrase mathematical climate, math climate, just like we call it the today's mathematical biology. And the MCRN was instrumental in mentoring a lot of graduate student postdocs and mentoring all the way for them to get into faculty positions. We have minority mentoring in there as well. It's a forum, it's a group that facilitates people from mathematics departments to get involved and get into research in climate science. Chris's own research is dynamic systems and nonlinear waves, and he has, for the past many years, been applying his expertise in dynamic systems in the data of simulation, basically how to simulate data into climate models. And today he will talk to us about challenges in data simulation.
Okay, great, thank you. All right, I'll have to hire you to give me intros all the time. Thank you. Let's see, am I on? Yeah, I'm on, good. All right, well, it's a great pleasure to be here. I find it kind of an honor to have been invited to give a plenary talk at this meeting, and I feel like I've come to a sort of family gathering, and it's a very warm and loving family. So I'm quite envious of the community you have that has been built up over the years through applied mathematics here. So I'm going to talk about data assimilation, which, as KK said, is to do with bringing data into models. I'll explain it in some detail. I've got various sort of credits here. A lot of my funding comes from ONR. This here with a little polar bear is, and the satellite, is the Nansen Environmental and Remote Sensing Center, which is in Bergen, Norway, and a lot of my collaboration is with them, and you'll see where that comes up. I wanted to start with talking about 2 great achievements, I think, of the last 50 years, and sort of contrasting them a little bit and thinking about, this relates perhaps to what we were talking about yesterday afternoon in the panel, what applied mathematics is about, and also how it's adjusting to the era of data science. So one is self-driving cars, and the other is the prediction of hurricane paths. While I think we're now perhaps somewhat obsessed with the novelty of self-driving cars and how wonderful they are and all of that sort of artificial intelligence side of things, we should not forget the incredible achievement that it is to actually be able to predict a hurricane path and generally to predict the weather and the situation with the environment in that way a few days out. This is the path of Katrina from 2005, and I don't know about the rest of you, but when Katrina was sitting down here, right, in the middle of the Gulf of Mexico, and they were predicting that it would take this right-hand turn to cross up over New Orleans and Mississippi, I was sort of, that'll never happen. That's just going to keep going straight. Surely they've got that wrong. But of course they didn't. They had it right on the nail. I was supposed to go to a meeting, actually, which was to be held in Stennis, Mississippi, right here, on the HICOM model. I was going to learn about HICOM, which is an ocean model that was and is still being used a lot in 2005. And luckily, the organizers canceled it on the Saturday evening, I think, in anticipation of Katrina, and Katrina actually crossed right over. I was booked into a B&B on Bay St. Louis, and on CNN on the Monday evening, I saw the owner of that B&B walking up and down the beach on the TV saying, "This was my B&B," and it was just absolutely devastated. And I read stories about the people who had stayed there and stayed on actually surviving by climbing up into trees and hanging on. So anyway, as you all know about the devastation of Katrina, but it was the preparations that could be made, which was afforded by the predictions. These kinds of predictions rely on our understanding of the physics and the encoding of the physics into models, right? They also rely on the inclusion of data to update those models, and that's what data assimilation is about. It sort of grew up, data assimilation, with numerical weather prediction. And this is a wonderful picture of an idea that was had by Fry Richardson. I think it was said yesterday in a talk, I think by Noah, that Bjerknes was the father of weather forecasting, which is true, but it was Richardson who actually sort of conceived of what has now become the sort of modern computational approach to weather forecasting. And this was long before computers were available, but he had this kind of image of people sitting in desks all the way around a replica of the globe, and each having their own little station where they would be fed data, and they would pass the data then to the person next door, and they would take it into account, basically somehow discretizing in using sort of human nodes instead of computer processors to actually advance the information and the forecast, right? So it was this sort of wonderful image of how this would work, and it was really quite prescient of the way that weather forecasting is actually done. There are two interesting books on this. All right, so data assimilation, what I really like about data assimilation is that it somehow balances equally models and data, the information that comes from these two sources. So you have on the one hand physical laws, like Newton's law of motion, which is underlying the Navier-Stokes equation, which is encoded in a model. And you have observations, which we think of as encoded in data. So when we talk about data in data assimilation, we do not mean the model output as data. We usually do not call that data. Data is what comes from measurements and observations. And then these two things are put together through data assimilation to get you an optimal estimate of the state of the system, right? Or a prediction thereof, right? So But the picture you want to have is that you're really getting a best estimate of the state of the system at a certain time for the purposes of using the equations then, or the computational model, if you will, to advance to the next time step and then include more data and keep going. Right? That's a picture you should have in mind. I want to distinguish a bit between modeling two different senses. One is a mathematical model, which is what we're all sort of familiar with and we think of perhaps as a model, where we write down equations, right? So partial differential equations or ordinary differential equations or whatever. These are the equations of geophysical fluid dynamics, which are basically Navier-Stokes with the Coriolis force and the various other different pieces that you need. So this is a mathematical model. The state variable here being governed is comprised of six variables: density, the three velocity variables, pressure, and temperature. And I want to distinguish that from what we think of as a model for the purposes of data assimilation, which is a computational model, which is basically a discretized version of the partial differential equations, right? Discretized on some grid, right? Which here was showing a sort of two layers overlaying a map of most of the United States. Although I notice this is kind of tacky, is that Seattle is actually cut off there. So. And the variables here are each of these variables here evaluated at certain times, but at each of these mesh points here, right, in the grid, right? So the picture you want to have is that the state in our model is actually a very, very large vector, right? And so it's not a function, it's a very large vector, which is indexed by each of the grid points in such a mesh. Okay? So that's the picture that you want to have, that our model is actually the computational model. So the advancing from this at one time tk to the next time tk plus 1 is actually achieved by solving the equations on the computer. In other words, it's technically, at heart, an algebraic operation that's taking you from one vector to another vector, a highly complicated one that is solving these PDEs in some sense. Okay? But that's what you want to think of as the model. So these are just some sort of examples, pictures here of different sort of gridded up systems. This is one from NCAR, which is Warren Washington is a researcher at NCAR. T85 is to do with the number of Fourier modes, which corresponds to the basically the resolution of this, and so can be thought of as the size of the mesh grids. This was one due to a postdoc of mine who now runs the data assimilation system at NOAA, Guillaume Vernier, where we were working on the Gulf of Mexico, and he liked to come up with really interesting grids. This is a picture from the IPCC, and this is a grid used by the European Centre for Medium Range Weather Forecasting in Reading in the UK. So how does data assimilation work? Okay, so as a mathematical procedure, it works as follows. You have a state vector, right? So again, this x in Rn you want to think of as this vector of these physical quantities at each of these grid points, right? And each one sort of concatenated with the other. So 1 6 after another 6 and so on, making up a very, very large state vector. And then the model will tell us how to get, oh, sorry, this should say xtk here, that's a typo. Will tell us how to get from the state of the system at time tk to the state of the system at time tk plus 1. I'm putting in here a p to represent parameters, because that's something that we may, under certain circumstances, want to vary, right? But the model is, again, this sort of algebraic operation in this computation that takes us from one time step to the other. But then at different time steps along the way, you have observations, right? So these are written in terms of another variable, y. You do not observe the entire state vector. You may, if you're lucky, observe parts of that state vector. You may observe temperature and so on, but there's absolutely no reason why you should be observing temperature at the grid points that the numerical method has provided you in the first place, right? So there's some kind of relationship between the state and the observations, and that's going to be an important issue here. So this is the picture you have. You start off at some initial condition at time t0. You go to time t1, time t2, and so on. This is the model running up here. But then you want to sort of input at each of these times here the observations. And you want to reset the state of your system before you enact the next model run by incorporating the information from those observations. All right. But so the other piece of the puzzle here, together with the model, is this relationship between the observations and the state vector, the so-called observation operator, which takes you from the state of the system to the observation space. Okay? Again, you might want to think of this as, you're measuring temperature, say. Temperature is one of your variables here. So this could be, if you happen to get temperature exactly at grid points, then this operation could be just a projection, right? But obviously there's no reason why your thermometers or whatever they are actually measuring temperature at a grid point. They're going to be somewhere else, so you're going to at least have to do a linear interpolation of what your model state has given you at the various sort of grid points. Okay, so just to sort of emphasize this point about how it all works, you've got model and observations, and you want to make a prediction. And you want to make a rolling prediction, an ongoing prediction. This is what numerical weather prediction does. And it was the success of this scheme that really changed weather forecasts that you see on the TV every evening from being a sort of seat-of-the-pants kind of intuition of the weather forecaster, which was, when I was a kid, was always just a big joke, to what they are now today, which is really with some non-trivial information and really is usually right. So here's the model then goes from T0 to T1. You make an observation. You go through some process of assimilation. You then update, and you get a new state of the system, which you then subject to the model again to take you to the next time, right? And then you go through that process again, and then you keep iterating that up to some end time that okay, or you just keep going. Right? So we've got the model, we've got the observations, right? We've got the different pieces I mentioned on the previous thing, and then we've got this assimilation step. So how does this assimilation step work? What's the mathematics underlying this assimilation step? Well, there are three different perspectives on data assimilation. They are all very intimately related to each other. However, they're based really on different points of view and different ways of looking at the problem, and they really lead to different ways of doing it. Even though you can go from one to the other and you can relate them to each other, and I will do that to some extent, they each give you a different way of looking at it. One is optimization. You've got two bits of information. You've got the stuff coming from the observational data and the information coming from the model. You try to sort of weigh them up. You have some confidence in the data, you have some confidence in the model, and you sort of balance them up, right? So that's an optimization problem. And in DA, the method is called the variational method. You may hear things like 3D var and 4D var. That's what they refer to here. The second method is an interpolation method, which says you've got two bits of information, you've got data here, and you've got model here, right? So somehow imagine drawing a line between them, and you would say your best estimate is somewhere on that line. Where it is on that line is weighted by your confidence in each of these two things, right? The data on the one hand and the model on the other. So that is what the Kalman filter is based on, which comes from control theory. But that is one of the key methods of data assimilation. And the third is a probabilistic point of view, which is the sort of conditional probability where you say, okay, I've got a forecast up to a certain point in time. I then introduce some observations into that, some observational data, and I want to get a new sort of, and each of those has an attendant probability, right? Think of them as PDFs rather than single pieces of information, which may be the means of those probability distribution functions, right? So, but you got one PDF giving you the forecast up to this point. You got a PDF which is for the observational data, and you want to get a PDF that combines the two things. Well, you use the law of conditional probability, which is Bayes' law. So this is Bayesian inference. Let me give you the mathematical formulae for these three things. So in this, the notation here, the forecasted time tk is going to be f sub k super f. F connotes forecast. The analysis is going to be the result of assimilating the data in. That's x upper a sub k. And the observations at time tk are y sub k upper o. That's an o, not a 0 for observations. Now you're going to express some confidence, right, in your forecast and some confidence in your observations. These will be expressed basically as error covariance matrices. B for the forecast and R for the error covariance. Okay, so the optimization method says what you should do is you should minimize this cost function, which on the one hand gives you your best your sort of inner product norm of the best estimate that the model gives you for the state of the system, and the other is what the weighing up what the model said the observations would have been, so you apply the observation operator to the model, minus, sorry, this should say xfk here, not just x. Oh, no, it says x, sorry, because you're minimizing this. Yeah, sorry. H of x minus what the observations are, right? And here your weight is given by this observation, the observation error covariance, and here the forecast error covariance. And then you take the minimizer of that, and the minimizer of that then should be your sort of best guess, right? That's the optimization approach. The interpolation approach says the analysis is going to be the forecast plus something in the direction of the data, right? So that's going to be some matrix here that you weigh. Remember, these are different dimensions, the y's and the k's, so it's not just like drawing a line of what's called the innovation, which is the difference between the observations and what the observations would have been if the model was completely capturing the observations, right? And you can show that this KK, which is the Kalman gain matrix, right, is given by this formula here, and H is the linearization of this H here, because this is basically a linear sort of theory, and B and R are these error covariances. That's what the Kalman filter tells you should do. Okay? But both of these approaches, in some sense, are based on the idea that you're looking for a best answer, right? And the statistician would say, but that's not true. You're not going to have a sort of best answer. All you're going to have really is a sort of a probability, right? So you're going to have you should be looking at PDFs, and that's what Bayes' theorem says. And it says the probability of the state of the system after the assimilation, given the data here, is proportional to what's called the observational likelihood, which is the probability that those observations will come up given the previous state of the system times the prior probability. Okay, sorry, this should say x, these should really say xk plus 1 here. Okay, so these are sort of three different ways of looking at it. They're very related because this posterior can be written as the exponential e to the minus j, right? If you have a linear problem here, if h is linear, this is a least squares problem, and you actually have one global minimizer, so this is fairly easy, and in fact, you can write this xk, this is a formula for that global minimizer, right? So that's the way these three different things are connected. But Bayes' theorem in a true sense is the most general because it does not assume that the distributions are Gaussian, which is tantamount to assuming that everything here is linear. It's related to that, right? Because if this were e to the minus j with a distribution, then well, you can think of that for yourselves. They would be Gaussian distributions involved, right? Yeah.
Could you explain, so for the posterior, you're conditioning on y, but for your observations, you're conditioning on x.
Right, so the observational likelihood is the probability that you would get those observations given the state of the system.
And for the posterior, like you want to make
Well, you want to find the probability for the state for x being in a certain state of the system given the observations, right? You could belabor it and say, well, also given the previous forecast too, but we tend not to do that. You tend to just apply this at one step. Okay? All right, again, these are the underlying models. Remember, this is the kind of thing that we're trying to model. But the key point here is that this state variable, right, is, as I said, comprised of the various physical variables listed at each of these grid points, and it can therefore be very, very high dimensional, right? It can be of the order of, well, in IPCC 4, it was probably 10 to the 6. In IPCC 5, that's the Intergovernmental Panel on Climate Change, in those kind of forecasts, it was 10 to the 9. It's probably 10 to the 12 now, right? So these are very, very, very big vectors, right? So you've got a real problem with dimensionality. If you are a Bayesian and you want to apply that probabilistic approach, then you would start talking about the curse of dimensionality. All right, so just to reiterate these different pieces, this is the setup, the model, and the observation operator are the two key mathematical pieces. This is, we're going to apply it sequentially, and these are the three different perspectives on how you do the assimilation. Okay? The two dominant methods, I would say right now, at least from the sort of research level point of view, this is perhaps not completely true from the operational weather center point of view, where the variational method is still probably dominant. But the two dominant methods in sequential data assimilation are the ensemble Kalman filter and the particle filter. The ensemble Kalman filter is a certain way of doing Kalman filtering where you use the nonlinear model system to create the covariance matrix. Okay, so this is the ensemble Kalman filter. It's a particular type of Kalman filter where we're going to find this KK in a particular way. Okay, the particle filter is basically an MC-MC approach to Bayes' theorem, to doing Bayes' theorem. So I want to give you an idea of how these two things work. Again, it's going to be a somewhat quick, superficial idea, but okay, so here's your Kalman filter formula. Here's your Bayes formula, right? You're going to be using this here, and basically, ensemble Kalman filter is going to tell us how to get this gain matrix, because remember, it has that formula, but we've got to unpack it, and this is, we're going to tell how to basically sample this posterior distribution. Here we're going to create this gain matrix using ensemble members. Here we're going to do it with what are called particles, which are weights. Both of these things are basically sprays of state vector points in the state space, right? I'll show you a picture of that in a second. What you do with these ensemble members on the left here is you evolve them under the model, right? Dynamical systems, people like me love this because it's just sort of evolving under the model, right? And this is a very dynamical systems sort of heavy point of view. Here you're going to evolve under the model similarly with some additive noise, right? So you're going to have to jiggle these around a little bit. Here you're going to create a covariance matrix P from the ensemble. In other words, my sort of B, my background error matrix, my covariance, my forecast covariance matrix, I'm now going to rename P because that's in this context, that's the standard terminology. And I'm going to create that from the ensemble. Over here, right, we just evolved these particles and we're going to have them form the prior. So think of this as a sort of histogram, right, where you've got a sort of bar graph at each of these particles, and this histogram is trying to approximate your probability, your prior probability distribution function before you do the assimilation. Right? Here you're going to update the ensemble using the Kalman filter with K based on this covariance P. So basically the two ingredients in the Kalman gain matrix are the error covariance and the observation operator in that sort of complicated formula. And you're going to do that update using that covariance that you formed from these ensemble members. Over here, you're going to weight the particles by the distance from the observations. It's a different procedure. And this is basically the way the observational likelihood is going to work. Okay, I'll show you a picture of how this goes. Here you get a whole new ensemble. Here you do not get a new ensemble, but you get different weights. So each particle has a weight, right? So you say, this is a good particle, so that's 5 high. This is not such a good one, it's only 1 high. And then there might be ones that are 2 high, and so on. Okay, and here you get a posterior PDF, which is basically what's approximated by this histogram. So you come in with a histogram with certain weights, and then you change all the weights depending on how close these points, these state vectors are to the observations when you look at the innovation, when you map H to them. All right, here's a nice picture of how that works. And you see the differences between the two setups. So this is the ensemble Kalman filter. You start with a spray. These are points in the state space, okay? These are the ensemble members. Over here, you have the particle filter. You have particles. So again, you just have a bunch of points, but they have different weights. You say this one is more important than this, right? So think of the histogram, a bar graph coming out of the screen with heights given by these weights. In each case, you apply the model to it, right? Now the weights are irrelevant in applying the model to it, and you get a new distribution down here, right? Because the model has moved these state vectors around, okay? Now what you do is really different in the two cases. Here you actually move these, and you move them towards the observation, right? Each one of them you move towards the observation. There's no weighting of these things here. They just sort of move towards the observation. And you can imagine then you've got a sort of new distribution here, right? And you can encode that in a covariance matrix. So this is what you end up with. This spray here. This process has led from this spray to this spray, okay? Now what you do here is you say, well, here's the observation. What I'm going to do is I'm going to reweight these things here according to whether they're close to the observation or not, right? So this one really close to the observation, it didn't have much of a weight before, but now it's going to get a big weight because it's really close to the observation. This guy, which came in with quite a weight, is going to get reduced in weight, right? Because it's far away from the observation, right? This is the way the particle filter works, and this is the way the ensemble Kalman filter works, right? And these are the two kind of trendy methods, if you will. All right, the problem here is nonlinearity. Because we're sort of representing this sort of probability distribution here, if you will, just by a covariance matrix, it means we're essentially putting a kind of linear straitjacket on this. We're sort of assuming that basically things are Gaussian, even though we're applying a nonlinear evolution here. The problem here is dimension, because this is very, very hard to deal with when you get to high dimensions. This doesn't work very well when you get to high dimensions. For various different reasons, you have to put a Gaussian PDF around the observation, and when you get to high dimensions, that becomes very, very localized. That's the nature of trying to get a mass distribution in very high dimensions, right? It's also true that these will get, spread apart and may look a very long way from this. Okay, so what happens, this is concretely the kind of thing that happens in this case that the nonlinearity will destroy the working of the filter here. What happens is that you imagine that there's a hole here. So suppose the nonlinear system has a hole, right? But the linear assimilation step puts these ensemble members into the hole. But that hole may have been a no-go area as far as the system was concerned. It might have said, that no state vectors go into that hole. Right? That would be a no-go area. But because going in the direction of the observation puts you into that hole, that will happen. Now, over here with the particle filter then, the particles can sort of collapse into a very small region, especially in high dimensions. So you can sort of see that maybe only one particle, or a very small number of particles, are close to the observation, and they get all the weight, and all the others are a long way away as far as the observation or probability is concerned. Therefore, they get no weight. So you get this collapse, and you end up with a sort of delta function PDF. Right, so if you want to see how the ensemble Kalman filter works, this is actually work of AMATH50 and myself, where we worked out this sort of going into this no-go area. This was basically in we're doing parameter estimation. We had a trajectory going around a sort of periodic orbit in the cellular flow field, and we followed this trajectory, and we had noise in the model and so on, and then we assimilated data which are observations of a different run, and we applied statistical methods to an ensemble Kalman filter. The green is the ensemble Kalman filter, and these were different observation sets, basically a different observational frequency, and this one was the same observational frequency as this, but a much longer trajectory. We thought maybe if you go longer, you can correct the problem. But actually what happens is the ensemble Kalman filter, if the observations are too infrequent, does not behave well at all. This vertical black line here is the actual truth at a certain time at the end of the run. But these other ones do very well. These statistical methods do well. What's happening here, this is the cellular flow field, this was the trajectory we were following. What's happening here is that after the first observation, your spray looks like that. So you've got kind of a Gaussian PDF. But before the second observation, after you've applied the model, the nonlinearity of the model has worked, which is actually the dependence of the periodicity from the center of the things, and you created a donut. Now, if you try to capture a donut by a Gaussian, right, that's going to be very, very sort of flat, and its mean is going to be in the center here, right? Or its mode is going to be in the center, right? And that's a problem. So what happens after the observation is then you end up with a very localized Gaussian around this, and you've thrown away all of that information from the model that came from the nonlinear evolution, right? So you've thrown this information away to have just this, right? And that's sort of a problem because you've lost all that nonlinear information. So I'm going to go through 3 challenges in the last 15 minutes or so. And I think these are mathematical challenges that are really interesting, and you know, we don't really ultimately know how to deal with them. It's very easy to state what data assimilation is with Bayes' formula or one of these other approaches, but to think of that as the end of the story of data assimilation is the same as thinking of the end of the story of fluid mechanics was when Navier-Stokes equation was written down, right? So that tells you how to formulate the problem, but there are enormous challenges in actually making, you know, coming up with the right way to do this in different situations. And the first is this nonlinearity versus dimension issue, right? The ENKF will work very well in high dimensions, right? It doesn't really bother it if you go to very, very high dimensional systems. What bothers it is if you go to very nonlinear systems. The particle filter will work well with these nonlinear systems, but will only really work in very low dimensions, right? I was working with a statistician, this was about 10 years ago, on applying the particle filter. There's been a lot of work since then on doing this, but we mentioned the idea of we were working on a 5-dimensional system, I think. We said, well, maybe we could do a 15-dimensional system. He said, oh, no, there's no way we could do that. That wouldn't work. But so here are various strategies for sort of straddling this divide of nonlinearity versus dimension. The first strategy, which I think is favored in the community, is to push the particle filter to the limits, right? To try to get ways to make the particle filter functional in high-dimensional systems. And there's been some very good work on this by von Leuven, Dan Crissan, and other people. And I mean, it's very, very good work. But my feeling is that it's playing catch-up all the time. It's trying to catch up with the current dimensional systems that are under use. And it probably isn't even catching up from 10 years back. But another approach, and this was thought through by, was a postdoc of mine who's now at the University of Surrey in the UK, is to sort of use a natural separation and a sort of hybrid approach. In other words, to try to get ENK, to try to divide the problem into a high-dimensional part and a low-dimensional part. And the high-dimensional part, you would use ENKF, and the low-dimensional part, you would use a particle filter, right? Sort of project into these two different pieces, but neither of them is closed, right? So you have to figure out how they're going to talk with each other. Sorry, I should also have mentioned Elaine Spiller in here, and also so there are some other people Elaine has worked with I should have mentioned here. Another point of view goes under the name of the augmented unstable subspace, which Alberto Carrassi has worked on a lot in recent years. And the idea is that the dynamics are really working within sort of a low-dimensional space. The problem is you don't know what that low-dimensional space is, right? This has underpinned an enormous amount of work in applied math, you know, about 20, 30 years ago, inertial manifolds and this kind of thing, where people, you know, tried to get hold of this low-dimensional behavior. And I mean, there's no universal prescription to where the low-dimensional behavior is going to exist, but you can use the dynamics to try to project onto that low-dimensional subspace, and then the idea would be to do data assimilation in that. So your model sort of forces you to have a low-dimensional part, and you try to identify it. There's some very good recent work by Eric Van Vleck and John McLean on that. And then there's an idea which we call coherent structure DA, and I'm going to go through that now a little bit. And the idea here is that if you look at this is a run, actually also in 2005. This is the Navy layered ocean model of the Gulf of Mexico. But you can see in the Gulf of Mexico that really the action in the Gulf involves primarily the formation of big rings. And these are like hurricanes within the water. And actually their connection with Katrina is quite strong because it was the presence of one of these things which contains a lot of warm water, which is a warm core, that Katrina passed over and was basically the reason why it went from a Category 1 storm as it crossed Florida to a Category 5 storm when it hit Louisiana and Mississippi. Right? So there are these sort of objects, these structures are really the players in the sort of fluid evolution in such an ocean model. So the idea is to try to project down onto the space of these coherent structures. And this is a paper involving myself and these two, both of whom were postdocs of mine, and appeared in Physica D in 2017. So we took a very simple problem, a sort of a toy problem, a meandering fluid jet, which is actually a cellular flow field on a beta plane, solving the GFD equations, and we ran that with noise, and this is a model for a sort of for a current here or a jet, and these are the sort of coherent structures. They're a bit messy, but that's because of the noise in the system, but that was necessary. And this is what trajectories look like. They will you can tend to distinguish the trajectories which start in these so-called gyres, these eddies, and the ones which are in the stream. And the idea is to try to capture these eddies here, and from, on the one hand, observations, and from, on the other hand, the model, and try to compare those two in the assimilation step. So how do you want to change the model in light of how well it captures the coherent structures, which basically are living in a low-dimensional thing because they're some kind of low modes, right? So what we do is we do a principal component analysis. The next step is to do a dynamic mode decomposition, a la Peter. And but we did this case a PCA analysis on the trajectory data. On the one hand, we took data from the drifter observations, and on the other hand, we took data from model-generated trajectories. These drifter observations, sorry, I'm using sort of ocean terminology here, thinking of this as in the ocean. These are following fluid particle trajectories, which, when they're measuring instruments, are sometimes called drifters. So here we get a data-generated coherent structure, and here we get a model-generated coherent structure, both captured in the sort of principal component space. So it's a small number of modes. We then compare those in the same way as in the particle filter. You're saying, you know, how close are these things? So you use something like the Hellinger distance to compare the generated coherent structures, and you have to use something called an approximate Bayes computation. This is statistically a bit involved, but it works, and it turns out you get actually considerable improvement with a small number of trajectories, right? We use just a small number of trajectories and placed them judiciously so they would capture the coherent structure, and you actually get an improvement over the particle filter, which is really considered sort of the gold standard as best you can do here, right? And you get an improvement over that using this, what we call the SMC ABC method. Okay, so that's one point of view, right? There are a number of points of view on how to deal with this nonlinearity versus dimension, but this is a major, major challenge. The second challenge, challenge number 2, what if you have a non-standard computational solver? Okay, so the thing we're particularly interested in is when you have an adaptive mesh solver. And this has not been dealt with in data assimilation, and you'll see why, right? So that says, suppose you have your mesh grid looks like this, that you're solving your PDE on, and supposing your grid points actually evolve, right? They actually move. It could be a Lagrangian solver where they're moving with the underlying fluid flow itself, or it could just be that you're deciding to move them into places where there are localized structures that you want to resolve. This is the problem we're motivated by. It's Arctic sea ice, and this is a model of the breakup of Arctic. You can see the breakup of Arctic sea ice. This is a next generation sea ice model due to Pierre Rampal, who's at the Nansen Center. And the great thing about this model is that it can actually capture open water and leads, which the standard models at the moment don't capture very well. So it's a model that includes the material properties of the ice. It's a finite element solver here that is used, but it's also Lagrangian. This is actually a comparison of a piece of the run against actual data observations, and it's quite sort of slow, but you can see how well it's sort of capturing this open water here. Okay, so our goal in this work is to develop a DA method for this solver, right? But this is an adaptive mesh solver. So it's a finite element model, as I mentioned. It's a Lagrangian solver, but it also has remeshing, because these triangles, these elements can get too distorted, and you then have to kind of reset them. And that involves taking away triangles and putting new triangles in, right? So grid cells are deleted and added at remeshing. Okay, so what you're getting in DA, the model is usually represented by an evolving state variable, as I mentioned. This is in Rn, where n is m times k, as I've sort of explained, where k is the number of physical quantities and m is the number of grid points. But your number of grid points now is actually changing. First of all, they're moving, right? That's kind of a problem, but they're changing also. The number is actually changing. That means that you do not have a consistent n here across time, right? So k is well defined, but m is not, right? Because it's changing in time because of the remeshing, right? And that's kind of, oh my goodness, data assimilation isn't set up to accommodate that type of anomaly at all, right? So this is a cartoon again of ENKF. The E index indicates ensemble members here. This is the analysis of the previous time step. You apply the model, you got a forecast, you're doing it on each ensemble member. Then there's this DA step, which gives you the analysis, and then you apply the model again. Now we got to figure out how to get from here to here, right? Where the problem is not so much that this may be a different dimension to this, but the dimension of this may depend on E, right? So for different ensemble members, you may have different dimensional state vectors, right? And you're trying to form an error covariance matrix using those things, right? This is our update here. This is our common gain matrix here using the error covariance and H. And the idea of the ensemble common filter is that you get this error covariance out of your system state here, right? But now the x1f, x2f, 1, 2, and so on, these are indexing the ensemble members. Each of these may be a different dimension. Now, that's not going to work, right? So you have to do something here, and the observation is basically, well, there's a principle here that the observation operator should not depend on the ensemble member. And you have to think about what that means for a minute. The observation operator should be unambiguous given the state of the system. But the state space could be different from the forecast and the assimilation steps, which suggests that what you should do is you should project onto some kind of reference mesh and use a reference mesh for the assimilation step. You pretty much have to do this. You're forced to do this. So we do a projection down here before we calculate the gain matrix and the innovation here, and then we project back. Okay? This projection back is actually a little trickier. And this is joint work with a group of at the Nansen Center, including Karasi and Rampal, and a graduate student of mine and a postdoc at the Nansen Center. So this is how the reference mesh would work in 2D. That's where we're actually currently working right now. The idea would be to have at most one vertex of each of the finite element grid in each mesh box, but that has to be across all ensembles. We're doing a 1D version of this, and I'll show you how that goes, where we're basically taking a projection now onto a sort of equipartition here, right, where these are the adapting grid points and these are the reference mesh points. And the idea is we take at most one grid point in each subinterval. So we tie the decisions you use for doing the remeshing to the nature of the reference mesh. So this is the procedure. You start with an initial ensemble, right? These are all of the same dimension. That's indicated here by these cards being all on top of each other. You do the forward model, you then have a forecast. They're all different dimensional, but then you map that onto the reference mesh here. You do the update, you get an analysis, and you map backwards, right? Sort of just a cartoon to show what I just said. We apply that to various one-dimensional PDEs to sort of test the system. We use Burgers and Kuramoto-Sivashinsky. Burgers because it generates a shock, and Kuramoto-Sivashinsky because it gives you chaotic behavior. Here you can see what the mesh looks like with Burgers, right? They're all converging on the shock here, and you see that as they spread apart, right, you have to introduce new ones here, right? But as they get to the shock, you start deleting them because they're getting too close to each other, right? So that's the kind of remeshing that occurs. If they get closer than, say, delta 1, you delete. If they get further apart than delta 2, you add. So this is how it goes then. You do this projection down onto here. We can do a high resolution and a low resolution mesh. The high resolution has delta 1, which is how close they can get, and the low resolution has delta 2. Both of these come from the remeshing criteria. Here you have to interpolate into missing cells because there'll be cells without values in them. And here you have to average over the grid points. These both introduce error, right? The question is, which is the worse error, right? So and you then end up with a system which has consistent dimension in each of the two cases, right? There was prior work on this by various people, but it's all very recent. There really hasn't been a lot on this yet. So this is Burgers and Kuramoto-Sivashinsky. This is the shock. This is chaotic dynamics. This is the picture for Burgers. You want to look at this high resolution RMSE versus the high resolution of the forecast, the analysis versus the forecast. So this is the blue line here for the high resolution forecast and the red for the high resolution analysis, and it improves it. And in fact, in the low resolution, it even improves it somewhat more, which is surprising but hopeful. This is Kuramoto-Sivashinsky. You can see quite an improvement. It doesn't converge because of the chaos in the system, but all right, the last challenge. Sorry, I know I'm extending your patience here, but this is important, and this is actually the place where machine learning ideas are going to come in, and I'm going to show my hand that I actually have a machine learning, an application of machine learning in this context too. The observation operator, I think, hides many sins, and it has not been dealt with at all. We tend to assume that somebody out there has really nailed it on the observation operator, and it's not something we have to worry about. We can work on the model side, and somebody else does the observation operator, and for mathematical purposes, we can just assume that that is a nice operation and the errors are Gaussian. This is the kind of just thing that we do. But the problem is the following. This is taken from a talk I heard last year by Jessica Matthews, who's at NC State and the National Center for Environmental Information in Asheville. And it shows rather nicely what the problem is. When you take satellite measurements, what you measure are intensity of radiance bands. So you're measuring radiation that is coming up from the Earth in certain frequencies. You are then interpreting from that things like temperature and ozone and water vapor and cloud detection and so on at certain altitudes. You're inferring it from the signature of the radiation bands at that level. So in each of these channels contains this information. So there's an inverse problem going from the radiances here down to this information that you're actually wanting. Now in data assimilation, we forget that it comes from radiances, and we just assume that our information is temperature and so on, and we say that's our observation and the errors are Gaussian. Okay. So the thing is, the radiances, right, come from the temperatures, but we really do it the other way around, right? We want the inverse problem. Okay, so this is sort of a picture of how we piece the thing together. I'm sorry, but in this model observation error field, they use W instead of X for the state of the system. But you could think of this as X. This is our forecast physical model. Takes us from one thing to the next to the next. F is like my M. This lives in the model space here. Over here, we have something that lives in the observation space, but that's our temperatures down here. What we really have are these radiance measurements here, the intensities of the radiation bands. And we have a function that takes us from here to here. We assume that these are our observations. Over here, we have initial condition error and model error. Over here, we have measurement error, which is error in the gamma case, but also observational model error, which is error in this inversion. We also have representativeness error, which is how we represent things in the model space in the observation space, right? So this is fraught with error, and we basically throw all this stuff into sort of a Gaussian. This is the initial condition model error is encoded in B, and all of this stuff is encoded in the R, right? Even though this could be very, very nonlinear here, it's solving a complicated inverse problem, but we sweep that all under the rug. Here's a way that manifests itself in sea ice. And this is really interesting, I think. So sea ice, what happens with sea ice is that the sun will melt the ice on top and turn it into water. And that creates what are called melt ponds, right? But under these melt ponds are ice. But if you look at that from a satellite, the signature of that is basically the signature of water. It doesn't see the ice underneath. So it can't really tell the difference between these melt ponds sitting on top of the ice and open water. This is 60% ice surface, 40% melt ponds. This is 60% ice surface, 40% open water. Same microwave intensities, okay? So how do you deal with that? So this is work of Christian Sampson is my current postdoc. This is an undergraduate of mine, and this is a graduate student at Minnesota of Dick McGeehee's. And this resulted from a project, an MCRN project that we started at the summer school last year in 2018. So this is part of the whole effort that KK mentioned in its current manifestation, right? Where anyway, so the question is, how do you deal with this? So the idea is that instead of doing the observation operator down in the temperature space, do it up in the radiance space, right? And machine learn the observation operator from the model space up to the measurement space, the observation space, as the radiances, right? If you do it down in the sort of projection of the model space, right, what you would do is you would sort of think that it looks like open water even though they're melt ponds, and you push the thing away from the truth in the observations. So if you use the real radiance measurements, you know, the radiance can't tell the difference between these two things, but it's not feeding wrong information, right? But it's hard to get these radiances. The model is very, very hard to get, but you're basically solving a forward model, and you can do that offline on all kinds of data sets and all kinds of, you know, situations that you can conjure up, and you can use that to train the observation operator. And this has been applied now. This is actually a very simple model due to Eisenman and Wetlaufer. It's just an energy balance model. And then they came up with proxies for observations and for the concentration. This was the machine learning, just to show you there really was machine learning in it. This is the neural net that was used. And the great thing here is I know nothing about machine learning. Christian Sampson knows nothing about machine learning, but the undergraduates do. They've all taken machine learning courses. So this undergraduate, Xiyang Jing, brought the machine learning into this process. And this is what happens here. This is the forecast using the traditional observation operator in this system here. And this is the forecast where we use the machine learned observation operator. This is the energy against time, converges very nicely. This is what's called the maximum attainable albedo, which is the other variable, and that converges to the truth very quickly. And here it doesn't, because you're constantly pushing it away from the truth by feeding it really misinterpreted observations. Okay, that was it. The conclusions are that I think DA is a critical technology enabling prediction. It balances models and data, treating them equally, and that's what I find so attractive about it. There are a number of challenges. I've talked about these three here. There are also understanding of dynamical effects, like drastic changes, tipping in the system. We don't really understand yet. I didn't discuss that. This is a rich field for new mathematical ideas and obviously important applications. I mean, I'm motivated by these climate applications, but biologists and neuroscientists are also starting to use this stuff a lot. So, okay, that's all I have to say.
I was just curious why you restricted your projection to have a single mesh point within your new grid. Why not end up with multiple particles inside your projected grid, your sort of reference grid? Why not combine them in some way onto that new grid and parse them across the grid?
Yeah, so that's, well, let's see. That's the low resolution case, right? So in the high resolution case, we do just have one in each grid cell. So we
move, they might coalesce into your reference grid to have multiple.
Yeah, but that would be before the next forecast. Okay. And then, yeah, then, I mean, anytime we use the high resolution reference grid, any state of the system will have at most one mesh point in each subinterval. Okay, and then the issue is how do you give a value to the intervals that do not have a mesh point in them, right? What was the question?
I don't know anything about coherence because I haven't taken time series, but I was thinking for the challenge number 1, I did take a statistical learning class, and we talked about the challenges of dimension reduction and nonlinearity. So I was thinking for dimension reduction, like could you try using like penalized regression, like ridge regression or the lasso, to reduce your dimension of your data set so that you can apply your particle filter?
Well, yeah, sure, but I don't know how well that's going to work in a highly nonlinear system. That would be the issue, right? I mean, I always think of something, like the Lorentz butterfly, right, where things are really getting twisted and contorted around, and I don't, if you just do two crude dimensional reductions, you can just project all this interesting dynamics out.
As far as the nonlinearity, could you fit like a spline or a basis function to try to capture nonlinearity in the data set?
Yeah, we think of the nonlinearity as mainly happening in the model, but of course, yeah, actually, I guess so. On the side of the observation operator, I mean, yes, I suppose that would be another way of doing this sort of machine learning step. Yeah, interesting idea.
Very interesting idea of using radiance instead of using temperature as the observation. Did I understand correctly that instead of doing data assimilation with inverse temperature inverse from radiance, you go forward with the model, and then you from the model produce a radiance to compare with the observed radiance? Is that?
That's right. That's right. That's right. So that would be, so your observation operator would take your state of the system, use the forward, which may have temperature or these variables. You have to figure those out, and then use the forward model to the radiances, and that would be your h of x, and then you would have the y. So that's your observation operator. But still, that operator itself is perhaps very difficult to get hold of. So you machine learn that operator.
The forward is a well-posed problem.
The forward is a well-posed problem, right? Right.
That's very smart. Any other questions? Okay, if not, let's thank Chris again for